Welcome to the Cabinet of Science and Fiction. Today we're diving deep into a truly fundamental question. What are the basic building blocks of our universe and the forces that govern them?
Yeah, it's a huge question.
We'll be exploring the fascinating history of this quest, from ancient philosophical ideas that honestly might surprise you, all the way to the cutting edge of modern physics, where reality gets really weird. So get ready for some mind-bending concepts as we unpack the mysterious world of fundamental constants and elementary particles.
It's a quest that really shows how our understanding has, evolved from these simple kind of intuitive ideas to incredibly complex, elegant theories.
Always driven by that core human thing, right? Wanting to know what everything's actually made of.
Exactly, that fundamental curiosity.
Okay, so let's unpack this right at the beginning. This search for the ultimate building blocks. I mean, it didn't just pop up in a lab somewhere recently, did it? You're saying it goes way back.
Oh, absolutely. Way back. Think about ancient Greece, maybe the 5th century BC. Yeah, without any of the instruments we have today, thinkers like Leucippus and Democritus were already thinking about this stuff. Like, if you take a piece of matter, can you just keep dividing it smaller and smaller forever?
Or do you eventually hit a wall, a smallest bit?
Exactly. And they landed on the idea of atoms, from the Greek atomos, which means, uncuttable.
It's uncuttable.
Right. It was purely philosophical back then, of course. Just this picture of tiny particles zipping around in empty space, bumping into each other, forming everything we see.
That's actually a radical idea for the time, thinking that solid stuff is mostly empty space and these little fundamental bits.
It was a massive intellectual leap, really. And then later, you get Plato, who was influenced by Pythagorean ideas about math and harmony.
Okay.
He connected these atoms to geometry. He sort of associated the elements, earth, water, air, fire, with specific geometric shapes. Platonic solids, actually.
Right, like cubes for earth, tetrahedrons for fire, that sort of thing.
Precisely. Suggesting that even these basic building blocks followed some kind of inherent natural laws. It was a step towards, rationally analyzing nature.
So instead of just saying the gods did it, they were trying to find a logical, unexplainable order. That feels like a huge turning point.
It really was. The rise of abstract thought back then, maybe even helped along by the development of the alphabet, allowed for this kind of thinking. The idea that reality wasn't just chaos, but could be understood through reason, that really took hold. And atomism was a key part of that shift.
Did this early atomic theory just sort of fade away then, or did it leave a kind of seed that sprouted later?
Well, it was kept alive, thankfully, and expanded on, actually, by the Roman poet and philosopher Lucretius.
Lucretius, okay.
In his work, De Rerum Natura, on the nature of things. It's this amazing epic poem.
A poem about atoms.
Yeah. And it meticulously detailed the atomic theories of Leucippus and Democritus, elaborated on them. But then, Rome falls, Dark Ages.
Yeah.
But then this poem gets rediscovered in the 15th century. And just around then, you get the invention of the printing press.
Perfect timing.
Incredible timing. Suddenly, these ancient ideas could spread like wildfire across Europe, planting the seeds for, the scientific revolution later on. Imagine reading this detailed atomic theory written over 1,500 years before.
Wow. So it was bubbling under the surface for centuries. But why didn't it become the main view back in the ancient world? Why did Plato and Aristotle kind of win out?
That's a good question. Plato and Aristotle offered more comprehensive philosophical systems, really. They tackled a wider range of questions beyond just matter.
Like purpose and ethics and all that.
Exactly. Their ideas about ideal forms and teleology, the idea that things have an inherent purpose, those resonated more strongly, maybe were easier to fit into the prevailing worldview. Lucretius's atomism, brilliant as it was, just couldn't quite dislodge these intellectual giants. It does make you wonder, though, if atomism had caught on earlier, maybe that long period of, let's say, limited scientific progress after Rome wouldn't have been quite so, long.
That long stretch where, Western thought seemed to take a bit of a detour, scientifically speaking.
Exactly. It was more dominated by dogma, less focused on empirical investigation. It really wasn't until the Renaissance, with that rediscovery of Greek thought, that the clarity of those early rational ideas was fully embraced again.
Okay, so fast forward quite a bit to the 19th century, and now we start seeing a real shift, don't we, from philosophy to actual quantitative science with atoms.
Absolutely. The 19th century was a complete game changer. Chemists started identifying more and more elements.
Right, the periodic table starts taking shape.
Exactly. And eventually, they identified over 100 distinct kinds of atoms. Now, that posed a major challenge to the original Greek idea of truly indivisible atoms. How could you have so many different fundamental building blocks?
Yeah, it's not very fundamental if there are 100 different types, is it? It's like finding an alphabet with hundreds of letters instead of just, 26.
That's a perfect analogy. And then early 20th century, we look inside the atom.
Rutherford and the gold foil.
Precisely.
Yeah.
And we find the nucleus with protons and neutrons. So another layer of complexity. The atom wasn't indivisible at all. It had its own structure.
Another blow to the original uncuttable idea.
A big one. Finding this tiny, dense nucleus with positive protons and neutral neutrons.
And then things got even wilder, right? Smashing particles together at high energies and creating a whole zoo of new particles. Where on earth did they come from?
Well, that was a direct consequence of Einstein's E and CFC phi.
Energy turning into mass.
Exactly. You pump enough energy into a collision, and poof, you can create new particles, new mass. It led to this explosion of discoveries. Some physicists at the time actually felt overwhelmed, comparing it to, like, botany with all its different species.
Just too many particles. Where's the simplicity?
It seemed like the fundamental building blocks were multiplying instead of simplifying.
But eventually, out of that apparent chaos, a more coherent picture did start to emerge. The Standard Model.
Yes, thankfully. The Standard Model came together as this remarkably successful framework. It organizes pretty much all the known elementary particles and the fundamental forces between them, well, except for gravity, all within a, relatively compact set of mathematical rules.
The theory of almost everything, some people called it.
That's the optimistic take, yeah.
Oh.
But almost is definitely the key word there.
Right. It's not the final answer. There are still big questions hanging.
Huge questions. The Standard Model, for all its incredible success, doesn't explain why particles have the specific masses they do. It doesn't include gravity, which is still Einstein's general relativity. And it doesn't really answer that deep philosophical question. Are these particles truly fundamental?
Or is there another layer down? Turtles all the way down.
Kind of. Or are they maybe just different vibrations of something even more basic, like strings?
Yeah.
That's getting to string theory. But yeah, the question of true fundamentality is still wide open.
And within this whole framework, these fundamental constants play such a crucial role, don't they? These numbers that seem to underpin everything.
They absolutely do.
Yeah.
Think about how we even define our basic units. Way back, Maxwell suggested we should base standards on microscopic things, like molecules, that are universally identical.
Instead of like a specific metal bar locked in a vault in Paris.
Exactly. And that idea is now reality. The meter is defined based on the speed of light, a fundamental constant. The second is defined using the vibrations of cesium atoms.
Because those things are presumably the same everywhere in the universe at all times.
That's the assumption, yeah, that these atomic and fundamental properties are truly constant. And the Standard Model itself has a bunch of these natural constants baked into it. They dictate the strengths of the forces, the masses of the particles.
But the crazy thing is, we don't actually know if they are absolutely fixed, do we? Could they change over time?
That's one of the really mind-boggling open questions. We don't have a definitive answer. Are they absolutely fixed constants of nature? Or could they possess some degree of freedom? Could they have been different in the early universe or even vary slightly across vast cosmic distances?
Einstein really believed they weren't arbitrary, right? That they were fixed by the deep structure of the universe.
He did. He felt strongly they were interconnected, fixed by the fundamental laws. But we haven't yet found that ultimate theory that derives them all from first principles. So, yeah, it remains a huge challenge.
Okay, let's dive into these fundamental interactions, the forces themselves. We've got gravity, the everyday one, electromagnetism.
Like electricity, magnetism, light.
And then the two nuclear forces, the weak and the strong.
Yeah.
The ones holding atoms and nuclei together.
Those are the four fundamental ways particles talk to each other, basically. Newton gave us the first mathematical description of gravity. Then Einstein revolutionized it with general relativity.
And Planck with quantum theory.
Absolutely. Planck's constant H ushered in the quantum era.
Yeah.
So you have these giants, Newton, Einstein, Planck, giving us the framework and the key constants. G for gravity, C for the speed of light, H for quantum mechanics. Central pillars of modern physics.
And then there's this other number that keeps popping up, especially in electromagnetism, this fine structure constant, alpha. Roughly 1 over 137.
Alpha. Yes. It's a dimensionless constant, a pure number, no units.
Which makes it extra mysterious somehow.
It does. It basically sets the strength of the electromagnetic force. And what's so fascinating and frankly baffling is its value. It seems arbitrary, plucked out of thin air, yet it's absolutely crucial for chemistry, for stars, for life as we know it.
Feynman called it a magic number, didn't he?
He did. Famously said it's one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. Really captures the feeling.
It really underlines how much we still don't know at the deepest level.
Totally. Feynman even joked that physicists should have 137 how little we know written on their blackboards. There have been attempts to derive it mathematically by Heisenberg, Euler, others, but nothing's really stuck. No compelling explanation for why that specific value.
And gravity, the force running the cosmos, how does its strength compare at the particle level?
Oh, it's incredibly, incredibly weak compared to the others down at that scale. You can quantify it with another dimensionless constant, alpha g, for gravity, and it's just astronomically smaller than alpha for electromagnetism.
So the gravitational pull between two protons is just negligible compared to their electrical repulsion.
Absolutely negligible. It's a huge difference in strength, and that hierarchy itself is another big puzzle in physics. Why is gravity so extraordinarily weak?
Now, our understanding of how these forces work changed dramatically with Faraday and Maxwell and the idea of fields. That was a big shift, wasn't it?
A profound shift. Before them, forces were often thought of as this sort of spooky action at a distance. Instantaneous influence across empty space.
Right.
Faraday and Maxwell imagined invisible fields, electric fields, magnetic fields permeating space. A charged particle creates a field, and another particle interacts with the field.
Not directly with the other particle across the void.
Exactly. And Maxwell's equations, they were just beautiful. They didn't just describe these fields, they unified electricity and magnetism and predicted electromagnetic waves, light itself, traveling at a specific speed, yeah.
And then quantum theory came along and said, well, these fields aren't smooth, continuous things either. They're quantized. They come in packets, photons.
Precisely. Which brings us to quantum electrodynamics, QED. It's the quantum field theory describing how charged particles, like electrons, interact by exchanging photons.
And it's sort of the jewel in the crown of physics theories, isn't it? Famous for its incredible predictive accuracy.
It really is. QED predictions for things like, say, the magnetic properties of the electron match experimental measurements to an astonishing degree of precision, like parts per billion. It's arguably the most successful, most precisely tested theory we have.
And this involves that weird idea of virtual particles, right? These photons that carry the force can just pop into existence.
That's a consequence of the Heisenberg uncertainty principle. Quantum mechanics allows for these tiny, fleeting violations of energy conservation over very short timescales.
Borrowing energy from the universe, basically.
Kind of, yeah. The photons mediating the force between two electrons, for example, are virtual. They borrow energy to exist for a tiny fraction of a second, transmit the push, and then disappear. It's happening constantly. That repulsion you feel is this exchange of virtual photons.
And Dirac's work was absolutely pivotal here. His equation not only described the electron relativistically, but also predicted antimatter.
Yes, Dirac's equation from the late 1920s was revolutionary. It combined quantum mechanics and special relativity for the electron. And out popped this prediction. There should be a particle exactly like the electron, but with positive charge.
The positron.
The positron. At first, Dirac wasn't sure, maybe it's the proton, but no, the math said same mass, opposite charge. And then, just a few years later, in 1932, Carl Anderson at Caltech actually found it experimentally studying cosmic rays. Amazing confirmation.
So these fundamental particles, electrons, positrons, photons, are they considered truly point-like in QED? No size, no internal structure.
That's the working assumption, yes. They're treated as mathematical points with intrinsic properties, charge, spin, mass. But, and this is a big but, quantum field theory also tells us the vacuum, empty space, isn't really empty.
The quantum foam idea.
Exactly. It's seething with activity. Virtual particle-antiparticle pairs, including electron-positron pairs, are constantly bubbling in and out of existence.
So a real electron isn't alone. It's surrounded by this cloud of virtual stuff.
Precisely. We talk about the naked electron, the theoretical point particle, versus the physical electron, which is the naked one, plus its entourage of virtual particles. This cloud actually screens the naked charge a bit, so the charge we measure is slightly less than the bare charge. It's called vacuum polarization.
And treating the electron as a perfect point leads to mathematical problems, right? Like infinities showing up in calculations.
It does. If you calculate the energy contribution of the electron's own electromagnetic field to its mass, assuming it's a point, you get infinity,
Hmm.
which is, not helpful.
Suggests maybe it's not really a point. Maybe it has a tiny size.
That's one possibility. Maybe it does have a very, very small radius, but we haven't been able to measure it. Experiments have pushed the limit down incredibly far. If it has a size, it's much, much smaller than a proton.
So how do physicists actually get sensible, finite answers out of QED if these infinities pop up?
Through a clever and mathematically rigorous set of procedures called renormalization.
Renormalization sounds complicated.
It is. But the basic idea is to absorb those infinities into the definition of things we can actually measure, like the electron's physical mass and charge. You sort of sweep the infinities under the rug in a consistent way, defining them in terms of the observed values, and it works astonishingly well. It gives finite predictions that match experiments perfectly.
Dirac also predicted the electron's magnetism, its magnetic moment, and QED improved on that.
Yes, Dirac's equation predicted a specific value for the electron's magnetic moment due to its spin. But later, extremely precise experiments found a tiny deviation from that value.
Uh-oh.
But QED, by including the effects of these virtual particles, these quantum fluctuations, could calculate that tiny correction, the anomalous magnetic moment, precisely. And again, the calculation matched the experiment perfectly. Another huge triumph for QED.
And QED has held up under intense scrutiny at high energies in particle accelerators.
Oh, yes. Experiments at big colliders like LEP at CERN and SLC at Stanford pushed QED into extreme regimes. Not only did it hold up, but these experiments confirmed another subtle prediction, that the fine structure constant, alpha, isn't perfectly constant.
Wait, what?
It actually changes slightly depending on the energy scale you're probing it at. It gets a tiny bit stronger at higher energies, exactly as QED predicts due to that vacuum polarization effect.
Wow. Okay. And finally, you mentioned QED is built on this idea of gauge symmetry. What does that tell us?
Gauge symmetry, especially local gauge symmetry, is really the fundamental principle underlying QED and electromagnetism. It's a bit abstract, but it relates to the fact that you can change certain mathematical properties of the electron's quantum field at every point in space and time independently if you also make a corresponding change to the electromagnetic field, the photon field.
So the electron field and the photon field are intrinsically linked by the symmetry.
Exactly. And demanding that this local symmetry holds requires the existence of a massless spin-1 force carrier, the photon. In a deep sense, the electromagnetic force is a consequence of this underlying gauge symmetry. It's not just put in by hand, it emerges from the symmetry principle.
Symmetry isn't just pretty, it dictates the forces. That's profound.
Hmm.
Okay, let's switch gears. To actually see this stuff, we need tools. We hear about energy units like keV, meV, JeV, TeV. Can you give us a sense of scale?
Sure. These are just ways to measure energy at the particle level. kV is kilo electron volts. meV is mega, or million. JeV is giga, billion. TeV is tera, trillion.
Okay.
So electrons in an old TV picture tube might have been tens of keV. Medical X-rays may be hundreds of keV. Nuclear reactions often involve meV. Particle accelerators like the Large Hadron Collider, the LHC, operate in the TeV range thousands of JeV. Higher energy means you can probe smaller distances, like using a microscope with higher magnification.
And way back, Rutherford's gold foil experiment, that was a key moment in seeing inside the atom, even without those huge energies.
A truly classic experiment. Around 1910, his team fired alpha particles, which are basically helium nuclei, quite energetic for the time, around 5 MeV at a thin sheet of gold foil.
And they expected them to just zip through, mostly.
Pretty much. Maybe slight deflections. But what they saw was astonishing. Most did go straight through, but a small fraction were deflected at large angles, and some, incredibly, bounced almost straight back.
Like firing a cannonball at tissue paper and having it bounce back, as Rutherford said?
Exactly. That led him to realize the atom's positive charge and almost all its mass must be crammed into a tiny, dense nucleus at the center. The electrons must be orbiting far out.
Which means the atom is mostly empty space. Still hard to really grasp that.
It is. The nucleus is maybe 10,000 times smaller than the whole atom. If you scaled an atom up to the size of a football stadium, the nucleus would be like a grain of sand in the middle. What you feel as solid is mostly electromagnetic forces between electron clouds.
And the energy of those alpha particles Rutherford used, that 5 MeV, was important?
Absolutely crucial. If they'd been much lower energy, they wouldn't have gotten close enough to the positively charged gold nucleus to feel that strong repulsion and bounce back.
Right.
If they'd been much higher energy, they might have just smashed into the nucleus, giving a different result. It's kind of a sweet spot for that discovery.
Now, as we go deeper into the atom and nucleus, our everyday intuition just breaks down, doesn't it? We have to rely on quantum mechanics.
Completely. Quantum theory just rewrites the rules at the microscopic level. Things that seem impossible classically, like particles tunneling through barriers, become possible. Uncertainty becomes fundamental. You can't simultaneously know a particle's exact position and momentum. It's often counterintuitive, even for physicists, but it works incredibly well in predicting how atoms and particles behave.
And quantum theory is actually what explains why atoms have a definite size and why they're stable in the first place.
Exactly. The size of an atom isn't arbitrary. It comes directly from that Heisenberg uncertainty principle. If you tried to squeeze an electron too close to the nucleus, pinpointing its position, its momentum, and thus its energy, would become huge and uncertain, blowing the atom apart. The atom settles into a lowest energy state, a balance determined by quantum rules.
And the electron's mass matters here, too.
Yes, the relatively small mass of the electron is key. If electrons were much heavier, atoms would be much smaller. If they were much lighter, atoms would be much larger. Quantum mechanics dictates the scale.
So quantum theory isn't just weirdness, it's the source of stability. It's why atoms of the same element are identical, why chemistry works, why structures recur in nature.
That's a really important point. The quantized energy levels, the identical nature of particles of the same type. These quantum features ensure that matter behaves predictably, forming stable molecules, crystals, and ultimately biological structures. Without quantum mechanics, you wouldn't have stable matter as we know it.
We also encountered this property called spin. It's like angular momentum, but intrinsic, not like a spinning top.
Right. Spin is a fundamental quantum property, like charge or mass. Electrons, protons, neutrons, quarks, they all have spin. It's quantized, meaning it can only take specific values. For these particles, it's spin 12. And importantly, its orientation is also quantized. A spin 12 particle can only be measured as spin up or spin down along any chosen axis. It's an inherent quantum angular momentum.
And Dirac's equation, we mentioned it predicted antimatter, but it also naturally incorporated spin, didn't it?
It did. That was another one of its triumphs. By unifying quantum mechanics and special relativity for the electron, spin just sort of fell out of the mathematics. It wasn't put in by hand. It was required by the synthesis of those two frameworks. And as we said, it predicted the positron, later found by Anderson. It's really a cornerstone equation describing these fundamental spin 12 particles, which still seem point-like despite having these definite properties like mass, charge, and spin. It's still a bit of a mystery, really.
Okay, let's go into the nucleus itself. Protons and neutrons. We now know they're not fundamental either. They're made of quarks.
That's right. They're composite particles. Protons and neutrons are made of smaller fundamental particles called quarks. The main ones for ordinary matter are the up quark and the down quark.
And the recipe is?
A proton is 2 ups and 1 down quark. A neutron is 1 up and 2 down quarks UD.
Now, there was an early puzzle, wasn't there? The neutron is slightly heavier than the proton, even though the proton has electric charge, which you'd think adds energy and mass.
That's a sharp observation. Naively, you might expect the proton's electric field energy to make it heavier. But it turns out the down quark is actually slightly heavier than the up quark. Since the neutron has 1 more down and 1 fewer up than the proton, that difference, plus subtle effects from the strong force binding them, makes the neutron just a tiny bit heavier. It's quite intricate.
And this whole quark model UD that was proposed independently by Gell-Mann and Zweig back in the 60s.
Yes, 1964. Murray Gell-Mann at Caltech and George Zweig, who was visiting CERN, both came up with this idea. They realized you could explain the whole zoo of strongly interacting particles, the hadrons, by combining just a few types of these fundamental things.
Which Gell-Mann called quarks, from James Joyce.
Exactly. A line from Finnegan's Wake. 3 quarks from Mustermark. That's why I actually called them aces, but quarks stuck.
And these quarks had those really weird fractional electric charges, plus 23 for the up, -13 for the down. That must have seemed crazy at the time.
Oh, completely. All known particles before then had charges that were integer multiples of the electron's charge, fractional charges. It was radical. A lot of physicists were very skeptical initially. Nobody had ever seen a fractionally charged particle on its own.
But the model worked incredibly well for explaining other particles, like those delta resonances.
Absolutely. The deltas are like excited states of the proton or neutron. Same quarks, but with their spins aligned differently. The quark model predicted their properties, their masses, their decays perfectly. That gave it huge credibility.
And the smoking gun, the direct evidence, came from those experiments at SLAC, the Stanford Linear Accelerator Center, late 60s.
That's right. Deep inelastic scattering. They fired high-energy electrons at protons. And occasionally, the electrons bounced off hard, as if they'd hit something small and point-like inside the proton.
Like finding marbles inside a pudding.
Exactly. And the way they scattered matched perfectly with hitting point-like particles with fractional charges, the quarks. It was a revolutionary discovery.
But we still never see quarks by themselves, do we? They're always stuck inside protons or neutrons or other hadrons. Confinement.
That's a fundamental feature of the strong force called color confinement. The force between quarks, mediated by gluons, behaves very differently from electromagnetism. It actually gets stronger as you try to pull quarks apart.
Like stretching a rubber band.
Sort of, but even stronger. If you pull hard enough, the energy you put in becomes enough to create a new quark-antiquark pair out of the vacuum, and they snap back to form new hadrons. You can never isolate a single quark.
And gluons are the particles carrying that force, the glue.
Exactly. Gluons are the force carriers for the strong interaction, exchange between quarks, holding them together.
And quarks also have this other property called flavor. Up, down. But there are more.
Yeah, flavor is just the physicist's term for the different types of quarks. We started with up and down. But experiments revealed heavier quarks needed to explain other particles. Charm, strange, top and bottom. 6 flavors in total grouped into 3 generations.
Okay, so beyond the everyday up and down quarks and electrons, we found these other particles, like the muon, Robbie's famous question, who ordered that? What was so puzzling about the muon?
Yeah, Robbie's quote really sums it up. The muon, found in the 30s, is basically a heavy electron, about 200 times heavier, but otherwise interacts almost identically. It's unstable, decays quickly, and it seemed to have no obvious role in ordinary matter. Why did nature make this heavier, unnecessary copy of the electron? It was a genuine puzzle. Still kind of is, in a way.
But antimatter, like the positron, that fits more neatly into eMMCO, right? You can just create electron-positron pairs from energy.
Absolutely. If you have enough energy, say, from a high-energy photon hitting something, you can convert that energy into the mass of an electron and a positron pair. Eve Z-Court in action.
Matter created from light.
Exactly. And the reverse happens, too. An electron and positron can meet and annihilate each other, disappearing and turning their mass back into energy, usually 2 photons, matter turning back into light.
So to study all this, to create these heavier particles and probe smaller scales, we needed more and more energy. Enter the era of particle accelerators. What's the basic idea?
Right, high-energy physics. The more energy you can pack into colliding particles, the smaller the structures you can resolve and the heavier the new particles you can create.
The simplest type is a linear accelerator, or LINAC, just accelerating particles in a straight line with electric fields.
That's the basic principle. You use strong electric fields to push charged particles like electrons or protons faster and faster along a straight tube, like an old TV tube, but scale up enormously in energy and length.
But you quickly run into limits with relativity, right? You can't get them faster than light, and it takes more and more energy just to increase their mass slightly.
Precisely. As particles approach the speed of light, adding more energy mostly increases their relativistic mass and momentum, not their speed much. The energy E becomes approximately equal to momentum P times the speed of light, C, EAPC.
So to get really high energies efficiently, circular accelerators, synchrotrons, were developed, using magnets to bend the particles around.
Exactly. Magnetic fields curve the path of charged particles. In a synchrotron, you use powerful magnets to steer particles around a ring, so they pass through the same accelerating electric field sections multiple times, gaining energy with each lap.
And we've seen a whole progression of these machines. The Bevatron, Fermilab's Tevatron, CERN's SPS getting bigger and more powerful.
Landmark machines, each pushing the frontier. Often using multiple rings, boosting particles from one to the next. A huge advance was superconducting magnets, which create much stronger fields, allowing higher energies in smaller rings.
And how do we actually see the results of these collisions? Detectors.
Crucial. Early on, things like cloud chambers or spark chambers let you literally see the tracks particles left. Modern detectors are huge, complex instruments, like giant digital cameras, layered with different technologies to measure the energy, momentum, charge, and type of potentially hundreds or thousands of particles flying out from a single collision.
And analyzing those tracks relies heavily on fundamental principles like conservation of momentum.
Absolutely vital. The total momentum before the collision must equal the total momentum of everything coming out. That helps reconstruct what happened, figure out if any invisible particles like neutrinos were produced, and measure the properties of new particles.
And to get the most bang for your buck in terms of creating new particles, colliding beams, head-on colliders, is the way to go.
Definitely. If you hit a stationary target, a lot of energy is wasted just making the debris move forward. If you collide two beams head-on, all the energy is available in the center of mass frame to potentially create new, heavy particles, much more efficient for discovery.
Early ones like the ISR at CERN, SPEAR at Slocky, and SPEAR was where that huge discovery happened in 1974.
Yes, the November Revolution. The simultaneous discovery of a new heavy particle, the Gypsy at SPEAR, an electron-positron collider, and Brookhaven, a proton accelerator. It was the charm quark peeking out, and it revolutionized particle physics. Electron-positron colliders proved fantastic for this kind of discovery.
Followed by bigger ones like Petra, LEAP.
Exactly. Pushing electron-positron collisions to higher and higher energies, allowing incredibly precise tests of the standard model at LEP.
And even colliders smashing different things, like electrons into protons at Hera in Germany.
Yeah, Hera was unique. It gave us an unprecedented view inside the proton, mapping out the quarks and gluons within it by probing it with high-energy electrons.
But there's a limit for circular electron colliders, isn't there? They lose energy just by going in a circle, synchrotron radiation.
That's a major limitation for light particles like electrons and positrons. When you force them to curve at high speeds, they radiate away energy as photons synchrotron light. And this loss increases dramatically with energy. It makes building even higher energy circular electron colliders extremely difficult and expensive. That's why people are planning future machines like the ILC, the International Linear Collider, to avoid that problem.
But for heavier particles like protons, it's less of an issue. So proton-proton or proton-antiproton colliders could go to higher energies.
Much less of an issue, yeah. Because protons are so much heavier, they radiate far less energy for the same curvature and energy. That's why CERN's first big collider discovery machine, which found the W and Z bosons, was a proton-antiproton collider, and why Fermilab's Tevatron could reach higher energies colliding protons and antiprotons, and why the LHC collides protons.
The discovery of the W and Z, the weak force carriers, at CERN was huge, right? Confirming the electroweak theory.
Absolutely monumental. A Nobel Prize-winning discovery that cemented the unification of the weak and electromagnetic forces. A huge success for the Standard Model.
Okay, let's dive into that strong force binding quarks together in more detail. The theory is quantum chromodynamics, QCD, analogous to QED, but different.
That's a good way to put it. QCD, developed mainly by Gell-Mann and Fritzsch in the early 70s, is the quantum field theory of the strong force, like QED is for electromagnetism.
And chromo refers to the color charge that quarks carry, not actual visual color, obviously.
Right. It's just a label for a new kind of charge that quarks possess. It comes in three types, whimsically called red, green, and blue. Antiquarks have anti-red, anti-green, anti-blue. Gluons, the force carriers, interact with this color charge.
And this color idea solved a big problem with the simple quark model, didn't it? Something about the Pauli exclusion principle.
Yes, exactly. Take a particle like the delta plus K. It's made of 3 up quarks, and their spins are all pointing the same way. According to the Pauli principle, identical fermions, like quarks, can't be in the exact same quantum state.
But they seem to be. 3 identical up quarks with identical spin.
Right, but if each up quark carries a different color charge, one red, one green, one blue, then they are no longer identical. They're distinguished by their color. Problem solved. Color charge provides an extra label, an extra quantum number.
And the symmetry underlying QCD, this color symmetry, is more complex than the one in QED, non-abelian.
That's a key difference. QED symmetry, called U1, is simple. It's abelian, meaning the order of operations doesn't matter. QCD's color symmetry is not abelian. The order does matter. Think about rotating an object. Rotating 90 degrees around the x-axis, then 90 degrees around the y-axis gives a different result than y first, then x. Color transformations are mathematically similar.
And this non-abelian nature has big consequences for the force carriers, the gluons.
Huge consequences. Unlike photons in QED, which are electrically neutral and don't interact with each other directly, gluons themselves carry color charge.
So gluons interact with quarks, but also with other gluons.
Exactly. There are 8 different types of gluons, and they interact strongly with each other. This gluon self-interaction is responsible for the most striking features of the strong force, like confinement and asymptotic freedom.
Okay, explain those. How does gluon self-interaction lead to confinement?
Well, think about the vacuum polarization effect we discussed in QED, where virtual electron-positron pairs screen the electric charge. In QCD, you have virtual quark-antiquark pairs, but you also have virtual gluons popping in and out. And the virtual gluons have an opposite effect. They effectively anti-screen the color charge.
Anti-screen. So the charge looks stronger from far away.
Exactly. The effective color charge, or the strong coupling constant alphas, gets weaker at very short distances, high energies.
Yeah.
That's asymptotic freedom. Quarks inside a proton, when they're very close together, act almost like free particles. But as you try to pull them apart, larger distances, lower energies, the coupling strength alphas gets much, much stronger.
So strong that you can't pull them apart. That's confinement.
That's confinement. The force just keeps increasing with distance, making it impossible to isolate a single quark.
How do physicists calculate things with this incredibly strong, complicated force?
It's tough. One major tool is lattice QCD. You place continuous spacetime with a grid, a lattice, and then perform massive computer simulations of how quarks and gluons interact on that grid.
And what do those simulations show?
They beautifully reproduce confinement. They show that if you try to separate a quark and an antiquark, the gluon field between them collapses into a narrow flux tube, like a string. And the energy in this string increases linearly with distance, meaning the force stays constant no matter how far apart you pull them. It takes infinite energy to separate them completely.
So the only things we see freely are combinations of quarks where the color charge cancels out. Color singlets.
Precisely. Baryons, like protons and neutrons, are made of 3 quarks, one red, one green, one blue, conceptually adding up to white or color neutral. Mesons are made of a quark and an antiquark, like red and anti-red, also color neutral. Only these color neutral combinations can exist as isolated particles.
Is it possible to have particles made just of gluons? Since they interact with each other, glue balls?
Theoretically, yes. Glue balls, bound states of pure gluons, should exist as color singlet states. But they are expected to be unstable and mix with other neutral mesons, making them incredibly difficult to identify unambiguously in experiments. There have been hints, but no definitive discovery yet.
And despite confinement, we've still looked inside quarks and leptons with accelerators, right?
Yeah.
To see if they have any substructure.
So yes, experiments, especially at HERA and the Tevatron and LHC, have pushed the search for substructure down to incredibly small distance scales, something like 10 to the minus 17 centimeters. Nothing so far. As far as we can tell, down to that limit, quarks and leptons still behave as fundamental point-like particles. Doesn't mean they are point-like, just that if they have a size, it's smaller than we can currently resolve.
Okay, let's try to pull all this together into the standard model picture again. It describes all these particles and forces except gravity. What are the main categories?
Right. The standard model organizes fundamental particles into fermions, matter particles, and bosons, force carriers. The fermions come in 2 types, leptons and quarks.
Leptons are the ones that don't feel the strong force.
Exactly. That's the electron and its 2 heavier cousins, the muon and the tauon. Each of these charged leptons has a neutral partner, the electron neutrino, the muon neutrino, and the tau neutrino. 6 leptons in total.
And we see that mass pattern again, electron, heavier muon, even heavier tauon.
Yes, this strange replication into 3 generations, each heavier than the last. Why 3? Why these specific masses? The standard model doesn't explain it. And the neutrinos, we now know they have mass too, but incredibly tiny.
That came from neutrino oscillations, right, them changing flavor as they travel.
Exactly. Experiments like Super Kamiokande in Japan and SNO in Canada proved that neutrinos oscillate, meaning they must have mass. It's very small, probably less than 1 electron volt, but definitely not 0.
And then the other matter particles are the quarks, which do feel the strong force. 6 flavors, also in 3 generations.
Right, up and down in the first generation, making protons and neutrons, charm and strange in the second, and top and bottom in the third, again, with increasing mass. The top quark is incredibly heavy, about as heavy as a gold nucleus.
So 6 leptons, 6 quarks, 12 matter particles grouped into 3 families. What about the force carriers, the bosons?
We have the photon for electromagnetism, the 8 gluons for the strong force, and then for the weak nuclear force, there are 3, the W plus S, the W and the Z boson.
And unlike the massless photon and gluons, the W and Z are really heavy.
Very heavy. Around 80 or 90 times the mass of a proton. This large mass is why the weak force is so weak in short range. It takes a lot of energy, borrowed via the uncertainty principle, to create a virtual W or Z to mediate the force.
And the electroweak theory unified the weak force with its massive WZ carriers and electromagnetism with its massless photon. That seems tricky.
It was a brilliant piece of work by Glashow, Weinberg, and Salam. They showed how, at high energies, these forces are different aspects of a single electroweak interaction with an underlying symmetry. That symmetry gets broken at lower energies, leading to the massive WZ and the massless photon we see. The theory also predicted interactions involving the Z boson, called neutral currents, which were later observed experimentally.
And the weak force, mediated by W and Z, is responsible for things like radioactive beta decay and letting heavier quarks decay into lighter ones.
Exactly. Beta decay, neutron to proton, involves a W boson. The instability of heavier quarks and leptons is due to them decaying via the weak force into the lighter generations. It's the only force that can change quark or lepton flavor.
And it has that weird property of preferring left-handed particles. Parity violation.
Yes, it's fundamentally asymmetric. The weak force interacts almost exclusively with left-handed fermions and right-handed antifermions. It treats mirror images differently, violating parity symmetry, unlike the other forces. A very strange but experimentally confirmed feature.
We mentioned the quark masses are important, especially the down quark being slightly heavier than the up. Crucial for stable protons.
Absolutely critical. If the up were heavier, protons would decay into neutrons, electrons, and neutrinos, and we wouldn't have stable hydrogen atoms. No stars as we know them, no chemistry. The universe would be drastically different. That tiny mass difference matters enormously.
And how does the Standard Model explain where any of these particles get their mass from? The Higgs mechanism.
That's the key. The Standard Model postulates a pervasive field, the Higgs field, filling all of space. Particles acquire mass by interacting with this field. The stronger the interaction, the more inertia the particle gains, the more massive it is.
And the Higgs boson, discovered at the LHC in 2012, is like a ripple or excitation in that field.
Exactly. Finding the Higgs boson was crucial evidence that this field exists, and the mechanism is likely correct.
But it still doesn't explain why the different particles interact with the Higgs field with such vastly different strengths, leading to that huge range of masses, from tiny neutrinos to the super heavy top quark.
That's one of the biggest holes in the Standard Model. It incorporates the Higgs mechanism, but the specific coupling strengths of each particle to the Higgs field, which determine their masses, are just input parameters. We have to measure them. The theory doesn't predict them or explain the hierarchy. Why is the top quark 350,000 times heavier than the electron? We don't know.
Interestingly, though, for the proton's mass, most of it doesn't come from the quark masses themselves, right? It's from the strong force energy.
That's right. The up and down quarks themselves are quite light. Most of the proton's mass, and the neutrons, actually comes from the kinetic energy of the quarks whizzing around inside, and the energy stored in the gluon field, binding them together, according to EMC-Cumlaw. It's mostly field energy, a QCD effect.
So the Standard Model, incredibly successful, describes almost everything we see in particle experiments, but it has these unexplained parameters, this mass hierarchy problem, no gravity. How many free parameters, constants we just have to plug in, are there? Around 28.
Something like that, yes, depending on exactly how you count free d neutrino masses. It's around 28 numbers, particle masses, force coupling strengths, parameters describing how quarks mix when they interact via the weak force. That's the CKM matrix. Numbers we have to determine experimentally and put into the theory by hand.
Which really motivates the search for something deeper, a theory beyond the Standard Model, like grand unification theories, GTs.
That's the idea. GTs try to embed the Standard Model's forces, strong, weak, electromagnetic, into a single, larger, more unified framework, governed by a larger symmetry group. The hope is that at some incredibly high energy scale, maybe 1016 GeV or so, these three forces would actually merge into one single force.
And that unification might explain some of these arbitrary parameters, reduce the number of constants.
That's the goal. A more unified theory should ideally have fewer free parameters and explain relationships between the ones we see in the Standard Model. However, GUTs are still very theoretical. We have no direct experimental proof for any specific GUT model yet.
Some GUTs make pretty wild predictions, though, like protons decaying.
Yes, that's a classic prediction of the simplest GUT models, like the SU5 model developed by George and Glashow. In these theories, quarks and leptons are put into the same mathematical structures, representations, and there are new super-heavy force carriers, sometimes called X-bosons, that can mediate interactions turning quarks into leptons.
Meaning a proton could decay into, say, a positron and a pion.
Exactly, violating baryon number conservation. Experiments like Super Kamiokande have been searching for this decay for decades. They haven't seen it, which sets extremely long lower limits on the proton lifetime, over 1,034 years, ruling out the simplest SU5 model. More complex GUTs, like SO10, might allow for longer lifetimes or different decay modes.
GUTs also predict that the strengths of the three forces should actually meet at that super high unification energy.
That's a key prediction. We know the coupling constants aren't really constant. They change with energy. They run. GUTs predict that if you extrapolate the measured strengths of the strong, weak, and electromagnetic forces up to the GUT scale energy, they should all converge to a single value.
And do they?
Well, almost. With just the standard model particles, they get close but don't quite meet at a single point. However, if you include the effects of supersymmetry, SU-SV, ACY, a hypothetical theory that pairs every known particle with a superpartner, the couplings do seem to converge beautifully. That's considered one of the main motivations for SU-TY.
And GUTs might even explain why the universe is made of matter, not antimatter, the baryon asymmetry.
That's another potential bonus. The early universe was incredibly hot, likely reaching GUT scale energies. The predicted super-heavy GUT particles, if they existed and had interactions that violated CP symmetry, treating matter and antimatter slightly differently, could have decayed in a way that produced slightly more quarks than antiquarks as the universe cooled. After all the pairs annihilated, that tiny excess of quarks would be left over to form the protons and neutrons we see today.
It's still amazing to think the strengths of forces aren't fixed numbers but change with energy scale.
It's a fundamental consequence of quantum field theory. Those virtual particle fluctuations constantly modifying the interactions depending on how closely you look. The rules really do change depending on the scale.
But the deepest mystery remains the particle masses themselves. Why these values? We still can't calculate the electron mass.
Nope, not from first principles. The standard model just puts in a parameter representing its coupling to the Higgs field. Why that specific value? No idea. It fuels speculation that maybe quarks and leptons aren't truly fundamental, that some underlying substructure might explain the mass pattern. Again, zero experimental evidence for that so far.
Okay, let's zoom out completely. To the cosmos. How do all these particles and constants shape the universe we see from the Big Bang onwards?
They're absolutely fundamental to cosmology. The Big Bang theory starts with this incredibly hot, dense state, so hot that initially even quarks and gluons were freely roaming in a quark-gluon plasma.
Before protons and neutrons even formed.
Exactly. As the universe expanded and cooled, quarks combined into protons and neutrons. A few minutes later, it was cool enough for protons and neutrons to fuse into the first light atomic nuclei, mostly hydrogen and helium. That's Big Bang nucleosynthesis.
And the predicted abundances match what we observe, right?
Remarkably well, yes. It's strong evidence for the Big Bang model. Much later, around 380,000 years, it cooled enough for electrons to combine with nuclei to form neutral atoms. That's when the universe became transparent to light, releasing the photons we now see as the cosmic microwave background radiation, the CMB.
And the tiny temperature ripples in the CMB, measured by satellites like Kobe, WMAP, Planck, those were the seeds of galaxies.
Precisely. Those tiny density fluctuations, amplified by gravity over billions of years, grew into the galaxies and large-scale structures we observe today.
The universe on large scales looks remarkably uniform, homogeneous, and isotropic, but that presents a puzzle too, doesn't it? The horizon problem.
It does. The CMB looks incredibly uniform in temperature across the entire sky, even between regions that, according to the standard Big Bang timeline without inflation, were never in causal contact. Light wouldn't have had time to travel between them to even out the temperature. How did they know to be at the same temperature?
Enter inflation theory, this idea of a hyper-fast expansion very early on.
Exactly. Inflation proposes an incredibly brief period of exponential expansion, maybe around 1035 seconds after the Big Bang, driven by some hypothetical inflaton field. This would have stretched a tiny, initially smooth and causally connected patch of space to become larger than the entire observable universe today.
Solving the horizon problem, everything we see was in contact before inflation blew it up. And it also explains why the universe seems so geometrically flat.
Yes, inflation naturally flattens out any initial curvature, just like blowing up a balloon makes its surface look flatter locally. Observations suggest our universe is indeed very close to flat, which fits well with inflation.
What about the Higgs field and cosmology? Does it connect to the accelerating expansion of the universe now, the cosmological constant or dark energy?
Well, the energy density of the Higgs field in its lowest energy state should contribute to the vacuum energy of the universe, which acts like a cosmological constant. The problem is, if you calculate the expected contribution from the standard model Higgs field, the value is enormously larger, like 120 orders of magnitude larger than the tiny cosmological constant value we observe driving the current acceleration.
120 orders of magnitude, that's not good.
It's arguably the worst prediction in the history of physics. It's a huge mystery why the observed vacuum energy is so incredibly small compared to theoretical expectations. Something must be canceling out the contributions, but we don't know what.
And inflation might not have ended everywhere, leading to the multiverse idea.
Some models of inflation suggest it could be eternal. While inflation ends in some regions, creating bubble universes like ours, it continues infinitely in the regions between them, constantly spawning new bubbles. This leads to the concept of a multiverse, an infinite ensemble of universes, potentially each with the different physical laws or constants determined by how inflation ended there.
Which brings us to the anthropic principle. The idea that we see the constants we do, because if they were different, we wouldn't be here to see them.
Exactly. If there's a multiverse with constants varying from bubble to bubble, then it's perhaps not surprising that we find ourselves in a universe whose constants happen to allow stars to form, planets to exist, chemistry to work, life to evolve. In most other bubbles, the constants might be wrong, leading to sterile universes. We are simply living where life is possible.
It's a potential explanation for the apparent fine-tuning, but it feels a bit unsatisfying to some, like giving up on finding a fundamental reason for the constant's values.
It definitely challenges the traditional dream of physics, finding a unique theory of everything that predicts all the constants. In a multiverse scenario, the constants we measure might just be environmental accidents, specific to our local bubble, not derivable from fundamental principles alone.
But do we have any evidence that the constants haven't changed over cosmic time, like from ancient natural reactors or distant quasars?
We do have some constraints. The Oklo Natural Nuclear Reactor in Gabon, Africa, operated about 2 billion years ago. The isotopic ratios left behind are sensitive to the values of constants, like the fine structure constant alpha back then. The data suggests alpha hasn't changed significantly since then.
Okay.
Also, astronomers look at the light from very distant quasars. The light has traveled for billions of years. By analyzing the patterns of absorption lines in the spectra caused by gas clouds the light passed through, they can look for tiny shifts that might indicate alpha was different in the distant past.
And what do they find?
The results are debated. Some studies initially claimed hints of a very small variation, maybe alpha being slightly smaller in the past. But other studies looking at different quasars or using different techniques haven't confirmed it. The consensus right now is that there's no compelling evidence for variation, and the constraints are getting tighter. But people are still looking very carefully.
The idea that something as fundamental as the speed of light or the electron's charge might have been different billions of years ago is just mind-bending.
It really is. It would fundamentally change our picture of the cosmos and its laws. But as I said, current evidence strongly suggests remarkable stability over billions of years. Laboratory experiments using atomic clocks also place incredibly tight limits on any present-day variation of these constants.
Well, that was quite a journey, a real deep dive through the building blocks of reality, from ancient Greek philosophers just thinking about atoms to the incredibly complex yet still incomplete standard model, and then these mind-stretching ideas about unification, inflation, maybe even a multiverse.
It really shows how far we've come, but also how much we still don't understand.
Absolutely. The fact that so many big questions are still out there, what are the fundamental constants, why these values, what's dark matter, dark energy, is there a theory of everything? It just highlights how much more there is to explore. Makes you wonder what breakthroughs are just around the corner.
Indeed. It's what makes physics so endlessly fascinating. The quest continues.
Thanks for listening to this deep dive into the mysteries of physics. Until next episode.